Okay, let's take a look at example number 3, which is the velocity of a falling ball. Now, suppose that a ball is dropped from the upper observation deck of the CN Tower in Toronto, which is 450 meters above the ground. And what we want to do is we want to be able to find the velocity of the ball after 5 seconds. All right, so through experiments that are carried out 4 centuries ago, Galileo discovered that the distance falling by any freely falling object is proportional to the square of the time it has been falling. Now, this model for free fall neglects air resistance. Now, if the distance fallen after t seconds is denoted by s of t and measured in meters, then Galileo's law is expressed by the equation. So this is a given information that we're going to need to know when we're talking about velocity of a falling object. So you want to make note that we're going to call s of t to be equal to 4.9 t squared. Again, that's a given information. Okay. Now, the difficulty in finding the velocity after 5 seconds is that we are dealing with a single instance of time, which is basically just t at 5. So no time interval is involved. However, we can approximate the desired quantity by computing the average velocity over the brief time interval of 1/10 of a second. So we can find out what's happening between t is equal to 5 to t is equal to 5.1. So since we're given, we want to find out what it is at t is equal to 5. We're going to explore the time interval of 1/10 of a second. So what happens from t is equal to 5 to t is equal to 5.1. Okay, so the average velocity is equal to the change in position divided by the time that has elapsed. Okay, so what we want to do is we're going to find out what happens when you plug in 5.1 into the function and subtract what happens when you put in 5 into the function. Okay, so again, because that's going to give you the change in the position over the time elapsed. Well, the time elapsed is going to be 5.1 minus 5. So again, you're using the rate of change here. Okay, so now substituting 5.1 into that function, so you're going to have 4.9 times 5.1 squared minus 4.9 times 5 squared, and 5.1 minus 5 is 0.1. Okay, and then when you multiply this all out, it's going to give you the value of 49.49, and that's meters per second. Okay, so if you take a look at this table, and this is our interval. Okay, similar to what we did in our previous example. Again, we were trying to find the values, okay, in a brief time interval of 1/10 of a second in between 5 and 5.1, and we determined at that particular point in time of that interval, the average velocity is 49.49 meters per second. Now, again, this table is showing the results of similar calculations of the average velocity that we have just done. Okay? It appears that as we shorten the time period, okay, the average velocity is becoming closer to 49 meters per second. So if we then shorten the time period here between 5 and 5.05, then you can see what's happening with the average velocity. Shorten it even more, and then even more, it's getting closer and closer to what? 49 meters per second. Okay, so what we can say then is that the velocity, okay, according to our table, at t is equal to 5 would be the following. We could say that the velocity is going to equal 49 meters per second. Okay, now you may have the feeling that the calculations used in solving this problem are very similar to those used earlier in the section to find tangents. Now, in fact, there is a close connection between a tangent problem and the problem of finding velocities. Now, if we draw the graph of the distance function of the ball, and then we consider the points, a 4.9a squared, and then qa plus h, we're adding h to the value of a, adding h to the value of a, okay, on the graph, then the slope of the secant line PQ would be the following. So it would be 4.9 times a plus h squared minus 4.9a squared over a plus h minus a, which is the same as the average velocity over the time interval in between a and a plus h. Therefore, the velocity at time t equals a, the limit of these average velocities as h approaches 0, must be equal to the slope of the tangent line P, which is the limit of the slopes of the secant lines. So here you can see the figures of what that looks like. Now, examples 1 and 3 show that in order to solve tangent and velocity problems, okay, we must be able to find limits. And so after studying methods for computer limits in the next 4 sections, we will return the problems of finding tangents and velocities when we get to section 2.6.